Good morning, all of you. Today we are going to continue with the chapter Moment Distribution Method. So first we will be going to have a brief overlook on what we did in the previous lecture. Then we are going to start with today's content. So all in all, in previous lecture, we have started with moment distribution method. In that we have seen two basic propositions. The first case was when my far end was fixed, and in second case my far end was pinned or simply supported. So during both the cases, we have evaluated two things mainly. The first was the relative stiffness of the beam, and the second was the moment that was transferred to the opposite end when I was applying moment at my near end. So basically talking, these were the two things that we did. First is when my far end is fixed. So by using our classic relation of slope deflection and radius of curvature, we have derived these two equations. So basically it was something like that. The stiffness of such kind of beam used to be 4 EI over L, and the moment or carryover moment used to be m by 2. So what was m by 2? The carryover moment. So if still you are confused about near end, far end, carryover moment or stiffness, I would like to repeat. See, this is my near end. A is my near end as I am applying moment at point A. So carryover moment is nothing but the moment that is getting transferred to the opposite end when I am applying moment at A. So here, which is my opposite end, as you can see, it is end B. So my carryover moment here will be half of this. So if I am applying MAB, MBA will be MAB divided by 2. So that is what you mean by carryover moment, and the stiffness we have derived to be 4 EI by L. So this was something that we have already done. So in this case, if you are having any doubt, you can ask. Similarly, we have also derived the same thing when my far end was pinned. So here, as you can see, when my far end is pinned, so what happens when my far end is pinned? If I'm applying moment MAB, the moment that is going to generate at this end is going to be 0. Why? Because here my end is a pinned or a roller or a simply supported, so it will not be able to carry any moment. So in this case my carryover moment will be 0, and the stiffness of such beams will be 3 EI by L. So these are the few things that you need to keep in mind. Here the stiffness will be 4 EI divided by L, and here my stiffness will be 3 EI divided by L. And how come this value came? So that if you want, you can refer the previous lectures. So you will be getting a clear idea. Now we will be going to do something really interesting. That is we are going to study the fixed end moment, how exactly fixed end moment is going to come into a picture. So here, if you understand the bending moment of a fixed beam, how it exactly goes. First, when a fixed beam is subjected to point load at a W, at a center which is having intensity W. So what, for my simplification, what I'm going to do is I'm going to divide this fixed beam into two parts. So basically I'm going to divide this fixed beam into two simply supported beam, and I should also consider that none of the effect is left out. So for that, what I'm doing, all the external loads I will be taking in the first case, and the fixed end moment that is going to be generated, that I'm going to take in the second case. So when you add up these diagrams, ultimately you will be getting the fixed beam diagram. So now, if I want to understand the bending moment diagram, what we are going to do? we are very well acquainted about the bending moment diagrams of simply supported beam. So in a simply supported beam, if it is subjected to a W, what will be the reactions that we will be getting? Obviously, as it is central point load, so here we will be getting it as W by 2. This also we will be getting it as W by 2. Here when I am taking the moment at this point, what happens? It will be minus M plus RB into L. So RB ultimately is going to be 0 because both the moment are going to compensate each other. Similarly, if this is 0, this also will be 0. Is it clear? So this is determinate structure. So determinate structure, we are very acquainted how to solve the determinate structures. So this both are my determinate structure. So in that we will not be facing any issue. Now, if I want to draw the bending moment diagram, what we will be doing? We will be simply, for the first beam, it is quite evident that when I am taking moment at the center, it will be W by 2 into L by 2. So that value here, it will be WL by 4. So this value will be WL divided by 4. So that will not be an issue. And also you need to consider the direction of the reactions. So if I am cutting a section here somewhere, what happens? Here it will be W by 2 and it will be clockwise. So ultimately this is going to be the shagging moment. So if it is a shagging moment, I am going to annote here positive sign. And here what happens is, if you cut any random section, suppose if you cut this section, I'm naming this as section 1, or if you cut this section which is section 2, or if you cut section 3, what is going to happen? In section 1, if I want to calculate moment, what shall I do? Either I need to take all the moments to the left or all the moments to the right. So if I'm taking all the moments to the left, what happens? See, the reaction is 0. So reaction into distance, but if my reaction is 0, distance does not matter. So if I am at this point, what will be the net moment? It will be M. And what is the direction of M? It is hogging. This is what we have already studied. If it is in this direction, we consider it as shagging, and if it is in the opposite direction, we consider it to be hogging. This is my section at which I am standing, or which I'm taking into consideration. So here, if I see the left side of this, so I need to refer the left, and this is my right side. So if I'm considering the left side of this, then it is going to be in this manner. So it is going to be hogging. And see, at section 1, the moment is going to remain M. If I am doing at section 2, what is going to be moment? Again, as it is already a moment, distance does not need to be multiplied with it, and distance will be multiplied with the force, but force is already 0. So here distance will not come into picture anyhow. So here also the moment will be M. Here also, if you go, the moment will be M. If you consider left, it will be M this way. If you consider right, it will be M this way. So ultimately, this moment is going to be a hogging moment. So this moment, if I am writing, the value will be M. Is that clear? So this is how I am drawing two different bending moment diagrams of the determinate structure, which I'm already familiar with. Once I'm doing this, the next step is quite simple. I will be simply superimposing both the diagrams, and I will be getting the final bending moment diagram of this particular beam. So how will I do that? Again, it's quite simple. Yes, this is how I will be doing. If I am going with the values, this will be M, this will be WL by 4, this will be WL by 4, and this is going to be M. Now, there is one interesting thing here. What happens is, if you consider the central region, this one, see that central region is coming in both the diagrams. It is coming in positive also, and it is coming in negative also. So what happens when it is coming in positive and negative? It is this moment is going to be 0. The trapezoid that I have showed by hatched lines is going to fetch me 0 value. So now I will be left with only negative and positive moment. So this moment will be my positive moment, and this moment is going to be my negative moment. Is that clear, all of you? So if I draw the net bending moment or net bending moment diagram, how it looks like? There will be a beam here. If you see what is the moment, as it is negative, I will be drawing below the line. Then as I am gradually going towards the center, the value of negative moments is decreasing. It is decreasing, and at this point it will be 0. So this will be 0. Then as you can see from this, the green portion starts. So that means I need to consider the positive moment. Then again it will be slowly decreasing, and at this point it is going to be again negative. So it will be negative, positive, or negative. So these are the two types of representation of bending moment of any given beam. The question that somebody asked me in the previous lecture, why the shape of this is rectangle. Now I guess all of you are clear with, because if the load is symmetric, then what happens? Both the supports will be having the same moment, and if the moment at MAB, this I will be writing as suffix AB, and this I will be writing as suffix BA. So if both this are same, then this also will be same, and if this is same, the diagram is always going to be rectangle. But in others, but in suppose the point load is not symmetrical, and if it is eccentric, then what happens? Sometime MAB will be greater, MBA will be less compared to MAB. At that time the diagram will not be a rectangle one, but rather it will be a trapezoidal diagram. Is it clear? So any doubts you can ask meanwhile. This is how we draw the bending moment diagram of a fixed beam. Any doubts, anybody, you can ask. I am unmuting all of you. If there are no doubts, we are going to proceed further. Now, as the chapter suggests, it is moment distribution method. So the major or the crucial part is going to played by this factor. That is what we call as distribution factor. Now, what exactly is the distribution factor? Forget structure analysis for a while. Now, what we are going to do is, there is a 100 kg weight which needs to be lifted. So for that, what I am doing is, what I'm doing is, I have taken three persons who all together needs to lift the weight of 100 kg. So first is a very strong man, the next one is a moderately strong man, and the last one is a comparatively weaker man. So what we need to do is, this three guys all together needs to lift a weight of 100 kg. So now my question is, in what proportions each guy will lift the weight? Is it going to be 33, 33, 33.33 all or not? So I'm again unmuting all of you. You can tell me your answer here. Yes, I want to hear it from you guys. No, yes, Pratik, I have unmuted all of you. You can participate in the discussion. So in what proportions the weight is going to be getting transferred?
Uh, Unsymmetric it will be.
Okay. So which man will be carrying maximum and which man will be carrying minimum weight?
Strong will be maximum.
Yes.
Weak will be
Weak will be
minimum.
minimum. Yes. It sounds to be very obvious that if there are three men with needs to lift a weight of 100 kg, all three will lift the weight according to their strength. So what I'm doing is, suppose considering that he is lifting say 50 kg, he might lift 30 kg, and the weakest will be only lifting 20 kg, isn't it? So this is how the distribution will happen. The same thing can also be applied to the structures. Suppose how it can be applied, that we are going to see in a while. If at a joint there are three members which are getting connected to each other, and all of them are having different stiffness. What is stiffness? That we have already seen. So if all three members are having different stiffness, then it is quite obvious that the more stiffer the member, the more moment it will carry. So the moment carrying capacity of all members is directly proportional to the stiffness. If stiffness is high, it is going to carry much movement. If stiffness is low, it is going to carry less movement. So this is how the moment distribution theorem is conceptualized. Any doubts here you can ask. If no, we will be moving further on. So now comes the moment distribution theorem. What it tells? It tells that a moment which is applied to a structural joint will be distributed among the connecting member according or in the same proportion as their stiffness. So the same idea which we have discussed earlier could be replicated for structural joints and structural members also. So for an example, what I'm doing here is, there is a joint which is getting connected to different members. So these are some three members that I have taken into consideration. Suppose this is a hinge support. This is again a fixed support. And this is again a hinge support. So on what factor the stiffness depends, that we should be very clear with first of all. So if we look at that, the definition of the stiffness or the formula of stiffness was, it was some constant, either 4 or it could be 3 into EI divided by L. So this is how the stiffness goes. Mind you, this is not 4 by 3. This is either 4 or either 3. You can consider any. So I am considering 4 as of now. If it is fixed, it will be 4. And if it is hinged, it will be 3. So it will be 3 EI divided by L. Now, if you closely inspect this formula, it depends on three parameters as such, the stiffness. First, it depends on the E. What is E? That is modulus of elasticity. The next one is I, that is moment of inertia. And the last one is L, that is length of a member. Is it clear? So on these three factors, the stiffness of beam depends. And in majority of cases, what happens, if my beam will either be of steel, then all the beams and columns will be of steel. Or in the other case, what happens, if my structure is an RCC one, all the members connected to joint will be RCC members. So if the material of all these three are same, then modulus of elasticity is going to remain same. Is that clear? So modulus of elasticity is going to remain same if all three members are made up of same material. So there is very little chance that modulus of elasticity will differ. What about moment of inertia? Moment of inertia will depend on the cross section dimensions. So if you talk about moment of inertia for a rectangle beam, it will be BD cube by 12. So it depends on the cross section dimension. So if this member is say 300 cross 300 and this is 400 cross 400, then what happens? Although the length of both this member are same, although it is made up of same material, but due to the change in cross section, of that particular element, the moment of inertia is going to change. And if moment of inertia is going to change, the stiffness is going to change. Is that clear? So this is how it goes with moment of inertia. And length of member, as you can see, it is inversely proportional. So the shorter member will be more stiffer, and as the length of the member increases, the stiffness of the member decreases. So that is all about length. So basically stiffness of any member depends upon these three important criteria, that is E, I and L. Now suppose I'm taking some random sections. So by analysis, what I'm getting is the stiffness of this member is high. So I'm writing it as a very stiff member. This is comparatively low. So I'm writing it as moderately stiff member. And this is less stiff. Is that clear? So these are the three members. The first is a very stiff member. The second one will be a moderately stiff. And the third is a comparatively less stiffer. So what happens exactly in the structure when I'm applying a moment of 100 kilonewton here? We are applying moment of 100 kilonewton meter at this particular joint. What happens? This moment will be transferred to each and every member. But how it will transfer? It will transfer according to the stiffness. So if this member is stiff, this will be carrying 50 kilonewton meter of moment. As in the previous case, the stronger main was lifting 50 kg weight. Here the same thing is applicable. The stiff member will be carrying 50, the moderately stiff will be carrying 30 kilonewton meter, and the less stiff will be carrying only 20 kilonewton meter. Is that clear? So this is what moment distribution theorems tells us. Is it clear, all of you? Any doubts you can ask? My next question is, how come we know that what proportion of moment will be distributed to each member? Here I have abruptly written 50, 30, 20, but the moment will be distributed, as I told, according to the stiffness. So for that, what I am going to do, I am going to introduce you to a new terminology, that is what we call as distribution factor. So it is nothing but the proportion of unbalanced moment carried by the each of the member. That means if there are three members, it is moment carried by each member divided by the total moment carried. So this is how it goes. Moment carried by each member divided by the total moment. So in our case, if I want to find out distribution factor of the first member, what I will be doing? What was the moment carried by the very stiff member? It was 50. So here mi will be 50. And what will be the total moment? It was 100. So 50 by 100 was 0.5. So distribution factor. And see, other definition, I can write it as, we know that what is moment? It is k into theta. So when if you remember the definition of stiffness, what was the definition of stiffness? It was action required to produce unit displacement. Yes. So in this case, what they are doing is, instead of s, they are writing k for stiffness. So action could be in terms of either moment or either force. Here I am considering action in terms of movement. So if I am taking action in terms of movement, what will be displacement? It will be in terms of rotation. So what happens? M will be equal to K into theta. Is that clear? So instead of Mi, I will be writing Ki into theta, and this also will be theta into summation of Ki. So theta will be cancelled out, and ultimately I will be left with distribution factor is equal to stiffness of individual member divided by the stiffness of all members, or cumulative stiffness of all members. So that is how we define distribution factor. Any doubts you can ask? Okay, fine. So very quickly we are going to look on the formulas of fixed and moments, because that is something that we require as an input when we are solving any moment distribution examples. The first thing what we are going to do is, although the beam is a propped cantilever or a continuous beam, the first step is to make each and every member as a fixed member. So when I am making all the members as a restrained member, there is going to be fixed in moment which is going to be generated. So what are the values of fixed in moment? So this is something that you already learned in your subject of analysis 1. So I'm going to rehearse that very quickly. So when there is a point load acting at the center, the formula will be WL by 8. So suppose if the load is 50 kilonewton and the length is 3 meter, it will be simply 50 into 3 by 8. Here also it will be 50 into 3 by 8. And make sure that the direction is always this. The beam will always be subjected to hogging moment. So first will be anti-clockwise movement and the second will be a clockwise movement. So this derivations you have already done in analysis 1. So we further does not need to go to the derivations of this formula. We can directly start with the formula itself. The next one will be eccentric point load. So what is eccentric point load? Point load which is not acting exactly at the center. So if my beam is of 3 meter, it may be possible that point load is acting either at 1 meter from this end, at 2 meter at the opposite end. So this is going to be the formula. So what will be the fixed end moment? It will be WAB square upon L square, and this side it will be WA square B upon L square. So how you will be remembering this? See, when I'm doing at end A, I need to look at the opposite. So what is the opposite span? It is B. So I will be squaring that term. And similarly, here I am going for B. So which is my opposite span? It is A. So I'll be doing the square of the A. So this is how you can remember this, because the derivation of the formulas each and every time will not be possible. So these are the first two cases. The next one will be when UDL is acting over the entire span, the movement at both the side, as the load is again symmetric, the movement again will be symmetric. So that will be WL square by 12. Clear? Where W will be UDL. If it is 15 kilonewton per meter, small w will be 15. L will be the entire length of the beam. So this is how it goes. Now I'm stopping for a minute. You all write it, the fixed and moments, because it will be a very important thing to start with any sum. So I'll be giving you a time of 1 minute. You simply write all these things, the three formulas. You draw the beam and write it. Written up till now. So the next thing is UVL. So when a UVL is given, what will be W? If suppose as it is a UVL, so here it will be 0, and here if it is 30, so W will be the maximum load. As it is the uniformly varying load, so load will continuously vary. So the maximum load will be my W. So see, when we tend to go to the maximum peak value, the formula will be WL square by 20, and on the opposite side it will be WL square by 30. So if it will be the reverse case, this formula is also going to switch. But mind you, till now the sign of the moments has not changed. Previously also it was hogging, till this portion it is also hogging. So if it is WL square by 30, so the end which is subjected to zero bending or zero load will be having 30 as a denominator, and the load which is having peak value will be having 20 as a denominator. So see, sometime what happens when you are solving a problem, sometime you will be having a load like this, which will not be a perfect UVL. It could be in terms of this. The load could be something like this. it may be say 10 here, 10 kilonewton per meter, and here when I'm reaching, it could be say 40. So how will I solve this kind of beam? Again, it's quite simple. What I'll be doing, I'll be dividing this beam into two portions. The first, we are going to take only UDL. So what constant amount of force is there? If you see, there is 10 kilonewton per meter which is acting constantly. So I'll be first drawing a beam which is subjected to a UDL of 10 kilonewton, and I will be adding it to the other beam which will be the pure UVL. So here what I will be doing, here I have already taken 10, so here it will be 0. So this point it will be 0, and here 40, but out of that 40 the 10 has already been taken, so I only need to draw UVL of this portion. This portion UVL only I need to draw. Clear? So here it will be 30. So again, it's quite simple. If you sum up both this, you will be getting the loading which is shown in the figure like this. So if you are knowing the formula of this, you simply need to add up the fixed end moment and you will be getting the fixed end moment of this particular beam. So this is how it goes. Any doubts you can ask further. Now it is eccentric concentrated moment. So see, this is something really important, because for the first time the direction of the fixed end moment has changed. When the beam is subjected to any kind of loading, the moment which is going to be induced will always be hogging. But here I have taken a different case. The beam is not subjected to a point load or any type of load. Here it is subjected to a moment itself. So when this kind of thing happens, it is very important to note the direction. So the direction will be in such a fashion. Suppose if this is a clockwise, this also will be clockwise, and this also will be clockwise. So when a point load, which when a concentrated moment acting in a clockwise direction, fixed end moment generated both the ends will be clockwise. Is that clear? And these are the formulas of the moments. So again, I'm giving you 1 minute time. You may copy it down. Okay, fine. So now, if I want to find out the reactions of all this beam, can anybody tell me how to find out the reactions of this? The moment, the fixed and moments we have calculated. But mind you, as it is a fixed support. So when it is a fixed support, there will be three reactions. There will be vertical reaction. There will be two moments. That value we can directly get from the formula. And as far as horizontal force is concerned, it will not come into picture obviously because there is no inclined load acting. So can anybody tell me? Yes, Solomon. Yes, I am unmuting all of you. Yes, Solomon, you can tell how to find out the reactions.
So I had a question about the L. The
Yes.
L isn't labeled in the L. The term L is not labeled.
Okay, L will be the total length.
Okay, sir.
Okay, L will be the total length. Now, yes, Solomon, can you guide me how to find out this reactions? I'm suppose naming it as RA.
Yes.
And if I'm naming it as RB, how will I find the reactions?
Use equilibrium conditions.
Exactly, very nice. See, what happens is, yes, Pratik, exactly, very nice, Solomon and Pratik. What happens when I'm getting these two values of MA, if I'm getting, and if I'm getting the value of MB, now my structure is no more an indeterminate structure. Once I'm getting these two values, my structure has been converted to a determinate structure. And if I'm having a determinate structure, I can easily put down the equilibrium condition and get the values of the reaction. Okay, so it is quite simple. So these are some standard cases. See, the diagrams that I was showing, they are not the only loading. The loading could be something different, but these are the standard cases. Your beam will be subjected to either of the cases in most of the cases, but sometime it may differ. The next one is fixed beam subjected to sinking. Now, first of all, when does a beam is subjected to a sinking? When does a support sink? Can anybody tell me? When does a support sink? You all of you have seen this. If there is a beam, it has been shown that this support will sink by delta. Say this is delta. So how come this support sink? See, when my structure is too long, that means it is this, something like this. These are all columns which are fixed at the base. Now when the structure is too long, the soil beneath the structure also will be different. That means suppose up till this point the soil may be some different, but as soon as shifting from this portion to this portion, due to any of the reasons, the soil is different. So what happens when the soil is different? There are the chances of differential settlement. So when this column, or when the differential settlement occurs, what happens to this particular beam? I am talking about this particular beam as of now, this beam. So differential settlement, that means due to load, if this soil is sinking by 1 mm, this will sink by 2 mm due to its ground condition. So what happens? This will be only sinking by 1 mm, but this portion will be sinking by 2 mm. So that case, my delta will come into picture. So here my delta would be 1 mm. Is this clear? So this is what we call as differential settlement, and sinking is always caused due to differential settlement of the soil. Now, when there is a differential settlement, the moment that is going to be generated will be 6 EI delta upon L square. Here again, the direction is quite important. I'll show you all the possible direction, how the settlement occurs and how should be the direction. See, the formula will always be same. It will be 6 EI delta upon L square. This also will be 6 EI delta upon L square. But here the major problem will be about the direction, this directions. So that I will not be sure of. So how will you decide the direction? Again, there is a trick to decide the directions also. What I will be doing is, if my beam, if say this support is going up by say 2 mm, so the derivations of this you have already studied in SA1, but if you are still facing an issue with the direction, what you are going to do is, you will try to make this beam in its standard shape. Yes, any doubts? Okay, so if I want to make this beam straight once again, what shall I do? I need to apply movement in this direction. Clear? So if I'm applying movement in this direction, the beam will again regain its original shape. So this is how I need to apply the movement. So this will be the direction of fixed end movement. Now if it is the opposite of that, that is this case. Then how the beam is deflecting? It is deflecting in this. Now again, if I want to make or come make the beam in its original position, what shall I do? I need to apply moment in this direction. So this will be the directions. Is that clear? Now in this case, what happens? The beam, the left support is sinking. So as to compensate that sinking, what shall I do? I need to apply moment in this direction so as to make the beam in its own position. So this is how the direction of fixed end moment in case of sinking is decided. Is that clear? Now the next one is the rotation. When a beam is subjected to rotation. So what happens when the beam is subjected to rotation? Suppose if my left hand support is getting rotated in a clockwise direction. So suppose the support is getting rotated in clockwise direction, then both the moment induced will always be clockwise. So that also you have proven in the previous semester. So no need to remember the derivations, but this sign convention you should be clear about. If this rotation is in clockwise direction, both the moments generated will always in clockwise direction. And see, the end at which the rotation is happening, I'll be terming that end as a near end. So this will be near end, and this end will be termed as far end. So if this is a near end, and this will be my far end. So moment generated at the near end will be 4 ei theta by L, and moment generated at far end will be 2 ei theta upon L. So if it is 4, here it is going to be 2. So it is as simple as that. What things you need to consider is you simply need to pinpoint the near end and far end. Once you are clear with the near end and the far end, the magnitude of the moment will not be an issue. The near end will be 4 ei theta upon L, and the far end will be subjected to 2 ei theta upon L. So again, I'm giving you one more minute. You can pen it down. Okay, fine. I guess all of you have completed with this thing. Now moving ahead, we are going to see a very simple numerical. Here what we are going to do is we are going to determine the distribution factor for the structure shown in below, and this structure is somewhat a very wayward structure. It looks something as shown in the figure. The structure is connected to member O. There are at a joint O, there are 5 members: OA, OB, OC, OD, and OE. The length of the members are different, the moment of inertia of all the members are different, and the support conditions of all the members are also different. So while calculating the distribution factor, we must be very clear that first step we should be evaluating the stiffness of each and every member. So suppose if you take OA as an example, so in OA what happens? OA, my far end is here, my far end is pinned, this far end is fixed, this is again pinned, this is again pinned, this is again fixed. So if my far end is fixed, the formula will be 4 ei divided by L, and if my far end is pinned, the formula would be d ei divided by L. Is that clear? So first of all, I'm simply going to write down stiffness of each and every member. So I have first I need to make a table like this. At first, I will be writing the joints at which all the members are meeting. So all the members are meeting at joint O. So I'll be writing joint O. How many members are there? There are 5 members. So I'll be labeling each of the members. Now we are going to write the relative stiffness that we have already done. So as far as OA is concerned, what is the condition? My far end is pinned. The formula will be 3 ei by L. So as you can see, the length is 4. So it will be 3 ei by 4. If you talk about the next OB, what is the condition? Far end is fixed. So it will be 4. It will be 4e. What is I? Instead of I, it is 2i. So I need to write 2i. So it will be 4e 2i by 5. If you are talking about OC, again 3ei by L. So 3e I is here. It is constant I. So I'll be writing I. And what is the length? 5. Similarly for this 3e, here I will be replaced with 2i, and as it is pinned it will be 3, and the length is also 3. Similarly I can do for and e OE. Again it is a fixed, so formula will be 4ei by L. 4 as it is, e as it is. Instead of I need to replace it with 2i. And what is the length? 4 meter. So this is how I can get the relative stiffness of each and every member. Once I'm getting all this, I'll be summing this up, so I'll be getting the total stiffness. So in that case, I will be simply writing, yes, what will be 3 by 4? It will be 0.75 EI by L, or EI 0.75 EI. Here what happens? It will be 8 by 5. 8 by 5 will be 1.6. So 1.6 EI. Here it will be 3 by 5. So 3 by 5 will be again 0.6 EI. Again it will be 3 to the 6 by 3. So that will be 2 EI. And last will be 4 to the 8. 8 by 4. So again it will be 2 EI. So what happens if I'm adding it? It will be 0.75 plus 1.6 plus 0.6 plus 2 plus 2. So you will be getting 6.95. Is that clear? So I have calculated the stiffness of all member. Then I will be writing the summation of all. And what is distribution factor? It is stiffness of each member divided by the total stiffness. So here it will be quite simple. It will be 0.75, or I shall write here. It will be 0.75 divided by what is the total stiffness? 6.95. When I am doing this, I will be getting 0.11. Similarly, here I will be writing 1.6 divided by 6.95. Similarly, for all this, if I'm writing, I'll be getting the distribution factors. And what does this distribution factor means? It necessarily means that the moment that I will be applying at O will be distributed according to this proportion. That will, OA member will be carrying 11% of my total movement, OB will be carrying 23% of my total movement, OC will be carrying 8% of the total movement, OD and OE will be each carrying 29% of the total movement. You should be always careful that when I sum up the distribution factor, it should be always equal to 1. The sum of distribution factor should be always equal to 1. So when you sum up, you will be getting 1. That means all the distributed moment, if I'm applying moment of 1, it is going to distribute in this proportion. But suppose in exam, if it is asked, the geometry is given, and if you are told what is the moment that is going to be distributed to each member, if central joint is loaded by 200 kilonewton meter moment, so what shall you do? You simply will be multiplying each distribution factor with 200. So that will be giving you an idea about what proportions of movement will be carried by each member. Is that clear? So this is all about today's lecture. Any doubts you can ask? You can unmute yourself and ask the doubt, or rather you can prefer chat box for asking doubt. I don't mind any of the method. So if I summarize today's lecture, we have learned something really important. First is distribution factor. The next one is moment distribution theorem. What does moment distribution theorem tells us? Moment distribution theorem states that when I'm applying moment at any joint, the moment transferred to each and every member will be in the proportion to their stiffness. Yes, Neil is asking. Yes, in your login you will be finding my video lecture, so that will not be an issue, Sam. Neil, why multiply by 200? Okay, fine. I'll tell you. Suppose if this is a joint O and if it is subjected to a moment of say 200, then I need to figure out, see, 200 is going to be distributed to each member. Yes. So in what proportion the 200 is going to distribute? So what I shall do, I shall simply multiply all this with 200. So I'll be simply writing into 200 into 200 into 200 into 200 and again here into 200. So when I'm doing this, the total if you make again it will be 200. That means what I'll be getting here, 200 into 0.11. Here I'm getting 22. That means the first member will be carrying, OA will be carrying moment of 22 kilonewton meter. Is that clear? So similarly, you can get the idea of all members moment carrying capacity. Yes, Nehal, am I communicating? Okay, fine. If there are no more questions, you can write your enrollment number in the chat box and make sure that all of you should write the enrollment number in chat box. Then only the attendance will take place. Then only your attendance will be considered. Okay, thank you. All of you have a nice day.